Hello, phenomenal ladies and gentlemen. It's Matafari here again, and welcome back to my space. This new video in the Concoction series is the first of a couple of videos where we go on an adventure into the world of complex numbers. In one of my earlier videos in the Concoction series, we already talked a little bit about the number systems. And we learned that the number system, the first of which we started mathematics with, or numeration with, are the set of the natural numbers. They are just the whole numbers. Then we know about the integers, the positive and negative whole numbers, including 0. This came to be because there was a problem with subtraction. Things like 3 minus 5 were deemed impossible to do before the invention of integers. Then, when the problem of division arose, we introduced the concept of rational numbers, the ratio of two integers such that the denominator is never 0. Then we have the irrational numbers that cannot be expressed as a fraction, like the rational numbers. And one of the distinctions between rational numbers and irrational numbers is when they are written as, apart from the fact that the irrational numbers cannot be expressed as fractions. So we have that when we express both of them as decimal numbers, the rational numbers, they are either terminating decimal numbers or non-terminating but recurring decimal numbers. What do I mean? So we could have, e.g., 2.5 terminates. That is a rational number. 1.3333 and so on is also a rational number. So this first one is a terminating decimal number, and this other one is non-terminating but recurring decimal number. Then, but irrational numbers, when we express them as decimal numbers, they are non-terminating but also non-recurring decimal numbers. For instance, square root of 2 is an irrational number, and that is 1.414 blah blah blah. The same thing with pi, which is equals to 3.142 blah blah blah, and e, which is the Euler constant, 2.178 blah blah blah. Okay, so these are rational numbers and irrational numbers, and when we combine these two together, we get what we call the real number. So the union of this set and this set gives us the set of the real numbers rather. So they are the points on the real line. So they extend from negative infinity to infinity, and these are the kind of numbers that we mostly have been dealing with from our elementary school days, our secondary school days. But now, in those days when a mathematician, especially Cardano, so he was working on some cubics problem, and he realized that he needed to get something for the square root of -1, especially when you have stuffs like x squared plus 1 equal to 0. To solve an equation like this, we know that the solution does not exist in the real number system, because there is no number that will square up to give -1. So if we have x squared equals to -1, no real number that is square is -1, because the square function is a positive function. So so he identified the solution to this equation as I. So we have I squared equals to -1, or I equals to square root of -1, and this I is what we call the imaginary number. So which is what makes up the complex number. So the complex numbers, denoted as C, is the set of all numbers of the form a plus bi such that a and b are real numbers and I squared equals to -1. These are the real numbers. So a and b, the real numbers, while together they form what we call the complex numbers. Okay, and any real number, this a is called the real part, and this b is called the imaginary part. So, and that is the story of the real numbers. And we have, as usual, the hierarchy or the chain of containment. So all natural numbers are integers. So all integers are rational numbers. So all natural are integers, all integers are rationals, all rationals are real numbers, and all real numbers are complex numbers. So even ordinarily the number 2 is purely real, but when I have 2 plus 3i, it has both real and imaginary parts, and if I just write 3i, it's purely imaginary. So before we start solving the questions, there's one more thing I would like to chip in, which is about the conjugate of a complex number. So the conjugate of a complex number, z equals to 2 plus 3i, is that complex number that will multiply by z, which is denoted by z bar, or that, such that the multiplication will give us a real number. And in this case, we have 2 minus 3i. We just change the plus to a negative number, just like we have the conjugate of surds, 2 plus 3 square root of 3, which is 2 minus square root of 3. So it is a conjugate such that when we multiply it together, 2 plus 3i times 2 minus 3i, using the difference of two squares, we get 2 squared minus 3i squared, and we know that this is 4 minus 9 times I squared, and by definition we know that I squared is -1, so this is 4 plus 9, which is 13. Now we can, with these few points, we can now start looking at the arithmetic of complex numbers. And when we talk about arithmetic, we are looking at the basic operations of addition, subtraction, multiplication, and division. So just like other numbers, complex numbers can also be added, they can be subtracted, we can multiply them together, and we can perform the division operation. So the addition and multiplication operation are just the usual way we deal with expansion of brackets or addition and subtraction that we know about. So in this case, the question is simply saying we should multiply all of this and put the final expression in terms of x minus yi. So we have 2 minus 3i, 3 plus 2i, 4 minus i. So we know that when we want to multiply things like this, we have to take it in, we take first pair, we multiply that, and we multiply it with the last term. So what do I mean? It's either I do these two first, or I do these two first. It doesn't matter which one I do first. So I'm going to take the last two. So where we have 3 times 4 minus I, the usual foiling, plus 2i into bracket 4 minus I. Then we have 2 minus 3i still outside here. So this gives us 2 minus 3i. Then 3 times 4, we know that is 12, minus 3 times I, 3i, 2i times 4, which is 8i, and 2i times I, which is minus 2i squared. And this is equal to 2 minus 3i, then 12, the negative 3i plus 8i will give us plus 5i, and we know that I squared is equal to -1, so 2i squared will be minus 2, then negative of minus 2 is plus 2. So this gives us 2 minus 3i, and 12 plus 2 is 14, so we have 14 plus 5i. And if we put this together, we're going to have again the same type of foiling we did. 14 plus 5i minus 3i and 14 plus 5i, and this will give us 28 plus 10i minus 42i, then minus 15i squared. Then again, this is 28 minus 32i. Then again, we know that I squared is -1, so -1 times -15 is plus 15, and that gives us 43 minus 32i, which is already in the form x minus yi, and we're done with that. So it's just the usual expansion of brackets that we know of. The addition, the subtraction, it goes the same way. So what we have basically seen here is multiplication and addition and subtraction of complex numbers. So the second question on the right here involves both multiplication and division. And if we have on this side, we have 1 plus I over 1 plus 3i squared. This is the same thing as 5 squared times 1 plus I squared over 1 plus 3i squared. I'm squaring everything. We remember that a plus b squared equals to a squared plus 2ab plus b squared. So it means this is going to be 25 into bracket 1 squared plus 2 times a times b, that's plus 2i, and plus I squared, all over the same thing 1 squared plus 2 times 1 times 3i, so that is 6i, then plus 3i squared. So this is going to give us 25 into bracket 1 plus 2i minus 1, because we know that I squared is -1. I think I've said that a lot of times now. So this is going to be 1 plus 6i, then 3i squared is 3i times 3i. 3 times 3 is 9. I times I is -1, so we have -9. So 1 cancels -1 here, so we are left with 25 times 2i on top over, then we're going to have 6i, 1 minus 9 is -8. So I can either write it like that or write -8 plus 6i. So I can easily see that 2 is common in the denominator, so I have 2 times 25i over -2 into bracket 4 minus 3i. So this reduces into -25i over 4 minus 3i. So we have done the squaring part. The next part will be the division part, where we do the conjugation. So you remember when you did SOD, radicals, you don't leave the radicals in the denominator. We do what we call rationalization, which is a process of making something that is irrational, making it rational. In this case, we cannot call it rationalization because we are not just making it rational, but it's the same approach. Here, we want to avoid a complex number in the denominator. So what do? We multiply both the numerator and the denominator by the conjugate of the denominator. And you recall what we said about conjugate. The conjugate of a plus bi is a minus bi. So in this case, the conjugate of 4 minus 3i is 4 plus 3i. So we do times 4 plus 3i over 4 plus 3i. So, and if we do this, so what I will do here, so I'm going to have -25. So I can multiply the I by the 4 plus 3i. We'll come back to that. So then for the denominator, we have difference of 2 squared. 4 squared minus 3i squared. So in the numerator, I have negative 25. Then 4 times I is 4I. Then I times 3I is negative 3. Because I times I is negative 1. So this is 16 minus, so we've done 3I squared before, which is negative 9. So this gives us negative 25 into bracket 4I minus 3 all over 25. So 25 cancels 25. And we are left with negative of 4I minus 3, which is the same thing as 3 minus 4I. And it's as simple as that. So we have shown how to successfully multiply. We have seen how to do division with complex numbers by using the conjugates to avoid the complex numbers in the denominator. Then, well, if you would like to see addition of complex numbers, it's as simple as it gets. So let's do 2 minus 3I, then plus 4I minus 3. So it doesn't matter, I'm just picking what we have here. Or let me write it exactly the same way it is there. So we have 3 minus 4I. So what do? It's just like we do with either surds or normal expressions that involve x and y, normal algebraic expressions. So you add the real parts together and you also add the imaginary parts together. So for the first one, the real part of this first complex number is 2, and the real part of this second complex number is 3. So we do 2 plus 3. Then we also add the imaginary parts. The imaginary part of the first one is negative 3I. The imaginary part of the second one is negative 4I. So 2 plus 3 is 5, plus negative 3I minus 4I is negative 7I. And that gives us 5 minus 7I. It's as simple as that. And when you need to do subtraction, the story is also the same. You deal with the real parts separately, you deal with the imaginary part separately. And with that, we've come to the end of this first part of the story we want to tell about the complex numbers. So the next time we come back, we're going to look at some questions that involve solving equations of complex numbers. So we will look at question number 3 and question number 4. And while you wait, I enjoin you to pick up some questions in the complex numbers domain and try to solve as many as you can. And pending that time, if you have any question or any doubt that you would like me to clear about complex numbers, do not hesitate to drop the comments in the comment section below. Till then, enjoy your time, enjoy mathematics. Bye.